Okay, on this one we're going to take a look at a very complicated problem. Now, some of the problems that we'll likely deal with are going to involve inclined planes, because those are very popular. Basically, an inclined plane is kind of like a very smooth hill. And I've got an inclined plane that is 30 degrees above the horizontal, and I've got a block on there that is 3 kilograms in mass. I'm going to call this guy mass 1. I've also got him tied across a pulley over here to mass 2, which is 4 kilograms. Mass 2 is hanging freely over the side. Now, one of the things that we'll probably do a bit more often is deal with this scenario where there is no friction. And then you can tell immediately that if there's no friction, well, this guy, he doesn't weigh as much. He's kind of like the two pulley, or the problem that we solved before with the two masses just on a pulley, except this time he's got some help from the inclined plane. This is going to be pulled down, it's going to drag him up, and they'll have some combined acceleration. But this time I'm going to introduce friction here, okay? And so I'm going to tell you that there is a coefficient of static friction of 0.5 between this block and the surface of the inclined plane, and that there is a coefficient of kinetic friction of 0.3. Okay? So we don't know if it's even going to start moving at all, because in real life, friction is going to try and keep this guy in one place. We don't know if it's going to be able to do enough to hold this 4 kilogram mass up. So that's going to be one of the things that we'll need to find out. I want to find out if they slide, or if they move, I should say, because only object number 1 is going to slide. If they move, if so, what is their acceleration? If not, how hard do I need to push it to move it? Or another way of looking at that might be, we could see how heavy of a mass we could put on this end, the dangling end, to find out when we would start moving that guy. Okay. Alright, so we've got an idea of what we're looking for. We've got some objects distributed in an unpleasant way, granted, but we know that we're dealing with forces because that's the name of the game here. We've been given some stuff about friction, that's a type of force. We've been asked about accelerations and forces. That's a big clue that we're going to be dealing with dynamics, with forces. So, what I need to do is I need to declare a coordinate system. Alright, well this is going to seem a little bit weird, but bear with me, because whenever you come across an inclined plane, what I'm going to do is I'm going to put my coordinate axis along that plane. I'm going to do positive x direction up that plane, because that way any of the motion that this guy has is up and down the plane. So that'll make it a bit easier on me. And at a right angle, so up at kind of a weird angle there, is my y direction. This may seem very strange, but this is the main thing that I've been talking about up to this point, where we have complete control over our coordinate axes. We want to change them to make the math easier on us. And you're going to see when I draw my free body diagrams in just a moment how that's going to make things much easier. Okay? Well, the last thing I need to do is I need to see what my coordinate system is like for this guy. He's just going to move up and down. But remember, I've already declared that I've got my positive x direction over here along the plane. And in that direction, that's where our wire goes, and it goes around this pulley, this frictionless pulley here. Okay, so our x direction actually gets bent downward, and this is going to seem a little strange, but in this case, down is plus x for this guy. Because if he moves a little bit down this way, this guy has to move a little bit that way. They're both moving in the positive x direction. I've got to make certain that the movement of one represents the movement of another in the same dimension. Okay? So, I've got that. Now I've got my drawing, I've got my coordinate axes. I know my masses, not much else. We've got some information about friction. So, let's go about drawing our free body diagrams. Okay, when I draw my free body diagram over here for object number 1, I've got a situation where I've got gravity, mass 1 times gravity down. Okay, I've got some tension up along an angle of 30 degrees, because it's going along the plane, so it's parallel to it. And I've got a normal force. Well, it's a normal force, so it's always at a right angle to the surface. That means that it is going to be up like this, with a right angle there. Okay? And this is my normal force. This is my tension. And, since we know that there's friction involved, this guy's going to be pulled this way, so we've got some friction. Either static friction that's holding him in place, or if this guy's pulling too hard and we overcome static friction, then it'll start moving and we'll have kinetic friction pointed off the other way instead. But that's one of the things we need to find out. Okay, well that looks a little messy, but we're going to see how it's useful to have our coordinate axes the way that they are in just a moment. Okay, so my free body diagram for object number 2 should be much easier. I've got in down, we've got mass 2 times gravity, our force of gravity, and it's being slowed down a little bit, pulled up by our tension. Alright, any other forces? None that I can see. So let's take a look at this. Now we've got our free body diagrams, we know all of our forces involved, we can start solving things, hopefully. But we need to be able to do something with those forces to get them into equations so that we can solve things. So, let's apply Newton's second law. I'm going to start off with object number 2 because he looks a bit prettier. I'm going to have sum of forces for object number 2. Sum of forces in the x, because remember, strangely enough, our x direction is actually pointed up and down for this object because of how we've set things up. So it's not y, even though yes it is up and down. This coordinate axis along the plane here is plus x, and this pulley has made it turn down bottom. So if this guy moves 1 meter in the plus x direction, this guy also moves a meter in the plus x direction. Okay? That's very important that we have that set up. So in this case, I'm actually dealing with my sum of forces in the x direction, even though it's up and down. I can label my dimensions or my directions however I want. I can put my coordinate axes wherever I want, whatever makes them easy for me. Okay, so in this case, since positive x is down, I've got a positive gravity minus the tension equals my mass times my acceleration. Okay, well that one wasn't as painful. Let's take a look at our sum of forces for object number 1 in the x direction. Okay, well in the x direction for this guy, he was plus x is that away, right? Well that makes that much easier, isn't it? I've got this tension that normally if I just had my coordinate axis straight to the right, I'd have to take my tension and I'd have to find the x component and the y component. I'd have to split up my friction into the x component and the y component. But because I've set up my coordinate system this way, this force and this force are completely in the x direction. I don't have to split those up at all. That's the entire point of, while it looks strange, setting it up this way. If you really want, you can stick with the regular plus y being straight up and plus x being straight to the right, but then you've got to split up this vector, you've got to split up this vector, you'll have to split up this vector. You wouldn't have to do anything to the gravity, but that's 3 different vectors that you would have to split up. That's going to make things look very unpleasant very quickly. But if we just tilt our coordinate axis up a little bit, where it's pointing along this inclined plane, well now this is completely in the x direction, this is completely in the x direction, this guy's completely in the y direction. The only thing that I have to split up is 1 vector. That saves me a lot of effort. I'm going to go with that. So, in the x direction, I've got in the positive x direction my tension, and in the negative x direction, I've got my force of static friction, or if this thing starts moving, that'll also be the force of kinetic friction. They'll just have slightly different numbers. Okay? And that's going to be equal to my mass 1 times my acceleration. I'm sorry, that's not in the y. We're dealing in the x, force of habit. Sum of forces in the x, sum of forces in the x. Okay, we'll take a look at our y direction, which is like this for this object. That's sum of forces. Oops. Look at me, I'm totally forgetting material. We're not done in the x direction. Because our x direction is like this. I've got my gravity, I've got a y component, and an x component of my gravity. The gravity is actually applying a little bit in the x direction since I've tilted my coordinate axes. Okay, well, this is 30 degrees because I'm up on a 30-degree incline. So you can imagine if this starts going down, then this guy's going to sweep over to the side and he would point straight down on level ground. And so this is 30 degrees. And so my x component, how much of it is in the x direction? Well, I've got 30 degrees here. I want to find the opposite side. And so I solve my vectors, and I would end up with my gravity in the x direction, so force of gravity in the x direction for this setup equals, what's that going to be? Mass 1 times g times sine, because I'm looking at the opposite side, 30 degrees. And my y component is going to be equal to mass 1 g cosine, 30 degrees. If you're confused about that, double check our vectors, make certain that you draw it out. We'd have a situation where here's mass 1 times gravity, that's my magnitude, my total length. I've got a y component here, and an x component here, with an angle of 30 degrees, and then solve for your y component and your x component. Okay? When you do that, you should end up with the y component is equal to the magnitude, mass 1 times gravity, times cosine, because that's our adjacent side, 30, and then the opposite side, our x component down here, will be the same thing with sine instead. So, turns out I wasn't finished because up here in object number 1, I've got a little bit of gravity pulling on it. I apologize for that. It is pulling it in the negative x direction, and our x component was mass 1 times g times sine of 30 degrees, and I'm going to set that equal to mass 1 times our acceleration in the x. Alright, so now, looking at our y's for object number 1, we've got, well, in the positive y direction, all of the normal force. We don't have to split that guy up. That's why we put our coordinate axes at their crazy jaunty angle. And then we've got our y component of the gravity, which is down, or in the negative direction of the y, I should say, not down. It's in the negative y direction. Minus mass 1 times g times cosine of 30 degrees equals mass 1 times the acceleration in the y. Okay? And this is another great thing because we've got a situation now where acceleration in the y, I can easily say, hey, is this object jumping up off of the plane or sinking down into the plane? Because y is at a right angle to our inclined plane. And so by setting my coordinate systems up this way, my acceleration in the y is going to be 0. Even if this thing starts sliding up the inclined plane the way I've set it up, all of that motion is in the x direction. So my acceleration in the y, because my 3 kilogram mass is not sinking into the plane or jumping up off of it, my acceleration in the y equals 0 meters per second squared, which means this whole thing goes to 0, and then I can add mass 1 times gravity times cosine of 30 degrees to both sides. And finally, solving my first equation, I end up with my normal force equals mass 1 times gravity times cosine 30 degrees. Well, that's probably going to be pretty important. Even though we're interested in the x direction, normal forces are usually important for for frictional forces, and we've got some frictional forces going on. So, let's take a look at our sum of forces in the x. So we've got a situation where now we know the normal force. Our force of static friction, that's a good place for us to start, is going to be the thing that will let us know if we move or if we don't. Okay, so what we want to do is we want to try and fill in this equation here. We know that our force of static friction is less than or equal to our coefficient of static friction times our normal force. Well, in this case, we're going to see if it's got enough to hold this guy in place. So we're going to go with, again, it's the lazy force. It will only do what it needs to. But if we're maxing it out, that means that this guy is going to become an equal sign. We're going to see if he can supply enough to stop this or not. Okay? So that'll be the most that static friction can give. And if it's not enough, then everything will start sliding. We'll have our first idea of the answer. We'd find out if they move. Okay? And then we'd need to solve for the acceleration. Or, if it turns out that static friction is plenty enough to hold it in place, then we know that they don't move, and we'd be able to solve pretty quickly for the amount of force that we'd need to get it moving. So if I take this guy over here, I've got, actually let's take a look at him. We don't know our acceleration in the x, that might be something that we want. We know our mass, we know sine 30, we know gravity, we know mass 1. So we don't know this guy. We have some information about this. We might actually be able to plug that guy in, but we don't know our tension. So even if we do know this guy, we've got two unknowns in our problem. We need to try and eliminate those. So let's real quick take a look at this. I'm going to take mass 2 times gravity minus the tension equals mass 2 times acceleration in the x. That's my other balance of forces in the x direction for my 4 kilogram block. I'm going to add my tension to both sides. And then I'm going to subtract my mass 2 times acceleration in the x, because I want to get the tension off by itself. Okay? So when I do that, I'm basically adding this guy over here and subtracting this guy over here. I end up with mass 2 times gravity minus mass 2 times acceleration in the x equals my tension. Okay? So, we've got a replacement for our tension. Let's take a look at this equation, the unpleasant one, that we now need to solve. We've got our tension, we've got an expression for our tension. Tension minus the force of static friction minus mass 1 times gravity sine 30 degrees equals mass 1 times our acceleration in the x. I'm going to start plugging things in. I know that my tension equals, I am rapidly going to run out of some room here. I'm going to erase this and this. So I've got a little bit of room. Hopefully that'll be enough. So I'm plugging in for my tension. I've got mass 2 times gravity minus mass 2 times acceleration in the x minus, I'm going to plug in for my force of static friction. I've got mu sub s times my normal force, which I look down here, is mass 1 times g times cosine 30 degrees. Alright, minus mass 1 times gravity times sine 30 degrees equals, and I've got mass 1 times acceleration in the x. Alright, well this guy's a little bit of a mess, so let's start plugging in some numbers so that we can cut down on this sum. So, I've got mass 2, well mass 2 is 4 kilograms, times 9.8. 4 times 9.81 meters per second squared. I end up with this guy. It's 39.24 newtons minus 4 kilograms times my acceleration in the x minus, we're going to evaluate this guy. Now I've got, I need cosine of 30. Alright. Times g, 9.81. So I've got cosine 30 times g times mass 1, which is 3 kilograms, times my coefficient of static friction, because we're going to look at friction, static friction giving all it can give and see if it's enough. Minus 12.74 newtons minus, I'm going to do sine 30 times 9.81 times mass 1, which is 3. .72 newtons. And that's going to be equal to mass 1, which is 3 kilograms, times the acceleration in the x. Okay, so now I've cleaned this up a little bit. I can add my 4 kilograms times the acceleration in the x to both sides. So I can get my accelerations by themselves. And I have 39.24 newtons minus 12.74 newtons minus 14.72 newtons equals 7 kilograms times the acceleration in the x. This was my static friction force. That's maxed out. So if the force of the tension pulling on my object number 1, is overpowering static friction and the bit of gravity that's involved, then we'll end up with a positive acceleration when we solve this. And if that's the case, it means that we've overwhelmed our force of static friction. Okay? Well, when I evaluate these, I take 39.24 minus 12.74 minus 14.72 equals, I end up with 11.78 newtons equals 7 kilograms times my acceleration in the x direction. Uh-oh. Our tension is stronger than our static friction and our gravity. So yes, this guy is actually going to begin sliding. So, if they move, we've answered yes, they move. Okay, so now we need to find the acceleration. Well, when they start moving, static friction isn't what's taking place anymore. We end up with kinetic friction instead. The moment it begins moving, we switch over from static friction, which had 0.5 as our mu or our coefficient of friction, to 0.3. So instead of the 12.74 newtons that friction would supply, when it starts sliding, mu S goes to mu K. Alright, so if I take a look back up here, everything else is the same. My frictional force for that situation is going to be force of kinetic friction equals mu sub K times the normal force. Well, that's pretty identical to what I ended up using up here. So, I'm going to take a look back here, and instead of the 12.7, which was 0.5 times mass of object 1 times gravity times cosine 30, I'm going to plug in 0.3 instead. So I'm going to do cosine 30 times 9.81 times mass of object 1, which is 3, times 0.3, which is my coefficient of kinetic friction, because now I'm sliding. And so now instead of this is my force of static friction. I'm going to replace that with the force of kinetic friction, because the things are going to move. We figured that out. So everything else is the same, 39.24 newtons minus my new value. Instead of using my coefficient of static friction, 0.5, I'm using my coefficient of kinetic friction. And when I solve that, I end up with 7.65 newtons minus my other term here, which is the force of gravity on the first block. That's unchanged. 14.72 newtons equals 7 kilograms times my acceleration in the x. So I add all of these up. Let me go ahead and do that. And there's a train going by in the distance. So I've got 39.24 minus 7.65 minus 14.72 equals, I end up with 16.87 newtons equals 7 kilograms times my acceleration in the x. I divide both sides by 7 kilograms. My handwriting is getting noticeably worse. I'm going to divide this by 7, and I end up with, finally, my acceleration is equal to 2.41 meters per second squared. Okay, like I said, this one's a complicated problem. Now for the AP students, this is the sort of thing that you want to be able to solve. We're going to need to put in some practice to make certain that you can solve these. These type of problems are likely to show up on the AP. There are some things that once you get used to them, we can deal with some techniques like reduced mass, that sort of thing that might be able to make them a bit easier. But this is the sort of thing that you want to be able to deal with. Often the way to make this much simpler is to ignore friction, and we could go through and split things up into components. We wouldn't have to worry about friction very much, but this is pretty much a very, very hard problem. Now in class, we'll be talking about inclined planes without friction so we can get an easier approach to moving our coordinate axes, which are pretty useful. Alright, but this is the full work on one of these more complicated dynamics problems.